Hi, welcome everybody to the third talk in this series, Perspectives in Mathematical Sciences, as part of the inaugural of the FC Kohli Center at CMI. So today we are delighted to have with us Sarah Shandera from Penn State. So she's the director of the Institute for Gravitation and Cosmos at Penn State. She did her PhD at Cornell around 15 years ago, and then she was a postdoc at Columbia and at the Perimeter Institute, and she's been at Penn State on the faculty since 2011. So Sarah is a cosmologist, and her main interest is in understanding the origin of inflation and understanding the connection between cosmology and particle physics. So today she's going to tell us about cosmology in the coming decade. Over to you, Sarah.
Great, thank you so much. Okay, great. Let me just get my pointer. Great. Okay. All right. Yes. Thank you very much for the invitation and the chance to be here. I'm really truly honored to participate with you all in these inaugural events for your center. And I have no doubt that this will be an enabler of really forefront and collaborative and international science in the years to come. So we all look forward to that. Oh, I see I'm not at the beginning of my talk. There we go. Great. Okay. So I want to tell you about cosmology today, and rather than give you a specific research talk, I really want to give you sort of an overview of where I think and sort of the consensus of the field is in terms of what will be the things to look for in the next decade or so. So I realize, sorry, my slides also don't fit the screen. So let me make sure they fit into the window. There we go. Good. Okay. So down here in the left, you see an educated artist's perspective on what we understand about the history of the universe. And you see sort of a bright blinding flash, which is this hot Big Bang that starts off the universe in a very hot, a very dense, and a very nearly homogeneous state. And then the universe cools and it expands, and these very small inhomogeneities grow under the action of gravity to produce this really rich structure that we have in the universe today, the late universe today. And so this is the picture that I want to talk about. And I want to start actually by remembering that the past decade has been a remarkable one for cosmology. So, sort of as a way of surveying what happened, you can look at the list of Nobel Prizes and you see something like 6 different ideas that were really new cosmological discoveries in theory and in observation over the past decade, ranging from black holes, both local black holes and general black hole formation, detection of gravitational waves, measurements of neutrino flavor oscillations that told us neutrinos have mass, measurement of the accelerating expansion of the universe. And I also added on here something that's not cosmology, but which has enormous import for cosmology, which was the discovery of the Higgs boson. So this is where we've been. And the question is, where are we going? And what I'd like to do is take this picture of the evolution of the universe and break it up into sort of, 3 eras where I think there are sort of 3 different types of questions, and in some ways 3 different types of data that we're going to look forward to in the next decade. So starting with the very earliest picture of the universe, how did it all get started and what happened at sort of the earliest times? This is really where we have questions that are sort of the foundation of physical law. What are the basic principles that we think tell us why we have the universe, or we should expect to have the universe that we have? And because things are at very high energies, we also think that sort of the interplay between quantum mechanics and gravity is important there. And you can ask, what is quantum gravity? We have no idea. Well, we have ideas, but we don't really know what the answer is yet. And there are different ways of posing that question, but one that I want to pose it is, why quantum? Why quantum phenomena and why gravity? And if we could answer those questions, we might know why we ended up with the universe that we have, that started in the state that it did. As you go, later in the universe and things cool, you get into a regime where really what's of interest is what is the spectrum of particles and their interactions. And really the chemistry of the standard model and whatever is out there in the dark matter is what turns those little initial inhomogeneities in density into this extremely rich and complex structure that we see all the way over on the far side of the screen over here. And once we get over here, we have this really rich structure of very complex dynamical systems. And the interesting thing is, how do you look at the dynamics and extract physics from all of that enormous rich data? And we're still seeing the universe in new ways, particularly with gravitational waves, And so we really have a lot to learn at this end of the picture. Okay, so that's the overview. So I want to start with the late universe, and I want to focus on the fact that it's a very dynamical universe. There are very short time scale, very energetic events that are happening, collisions of objects, explosions of objects in these complex systems. So, one of the things that we're doing is just we're able to survey what's out there. What is the spectrum of truly unusual states of matter that the universe has formed for us, and what do we learn by studying those? There's a second thing, though, that we learn, and that's related to the fact that over the past decade, people have categorized to an even greater degree this sort of steady rain of very high energy particles, so high energy cosmic rays, protons, various things that come filtering in from space, and very high energy neutrinos that also are sort of steadily raining down on us. And we don't know what the origin of all of those particles is. It's sort of a steady rain, but in principle, by studying these very complex events, we might be able to get some insight into what the origin of all of these particles is. And that informs both, why do we see this rain, and what is the physics of these very complex structures. So famously, 2017, in one of what was science's breakthrough of the year, saw the observation of the first time we detected the merger of neutron stars. So neutron stars, extremely compact objects in this sort of very special nuclear state of matter, are stellar remnants. So they're really sort of a canonical object that's the result of this very late time universe where you have these complex structures. And two of these things smashing together was, caused such a disturbance in space-time that was detectable by our network of gravitational wave detectors. But there's also a very complex matter environment around these, right? There's a lot of matter that's sort of in the vicinity of these things. They are themselves this interesting nuclear state of matter. So you also get this very rich spectrum of electromagnetic radiation and probably other particles emitted from this collision event. So of course, the fact that this happened at all was really enabled by the fact that we're in this new era of gravitational wave detection. It's only been, about 6 years since we first were able to detect the collision of two black holes. And in that time, the number of detected mergers has grown to about 100. And this is thanks to this really worldwide network of gravitational wave detectors, a network that's still growing with COGRA and LIGO India, and a network whose sensitivity is increasing, very systematically. So that means that one of the things we have to look forward to in the next decade is a really significant increase in the number of detections of gravitational wave events. So this binary neutron star merger is really just a subset of these really fascinating events that are new in the past few years. What happened with the neutron star merger is that it wasn't just gravitational waves. In other words, how do we know it was neutron stars and not a black hole? We know because there was this incredibly rich follow-up campaign where people observed across the electromagnetic spectrum sort of the remnants of this collision, right? All of the aftershocks. So you can find this image on the archive, and all of these little colored lines are actually going off to images of some of the data. So it's a very interesting image. But what I wanted to point out for the purposes of this talk are three things. First, you see not just gravitational waves, but across the electromagnetic spectrum. And you see that observations presented here are really in the timescale of days. And in fact, observations of this event continue even to now. So it's an extremely rich and useful event. The other thing to notice is the sheer number of observatories and collaborations involved in this operation, right? You can see them all listed here. In fact, if you look at the paper and you are so foolish as to click on show full author list, you will have an enormous loading problem, because this paper had participation from something like 70 international scientific collaborations, and it was estimated that something like a third of all professional astronomers or astrophysicists worldwide participated in this event. So this is not just a fabulous science event, but a really extraordinary social event, right? This is the era of true international global collaboration where we need coordination across, thousands of individuals and worldwide, and many, many, many collaborations. A second event of that type, which also happened in 2017, was a signal from what turned out to be a blazar, so a galaxy that's got a very active central black hole, and it has these big, jets of powerful radiation that's pointed nearly toward us. And there was a detection of an unusual high energy neutrino event by the IceCube collaboration, that's indicated here. And then again, IceCube was able to send out an alert for this process, and many other facilities also took a look. And again, you can see this sort of over a time scale here, it's about a month, and detected electromagnetic radiation from the same event. So similar in the sense that there's one detection made by a facility, an alert goes out to the community of astronomers, and then many instruments can eventually point in that direction and confirm that we're seeing correlated phenomena in particles and radiation from the same event. So this is really one of the big ideas for the next decade, which is this multi-messenger astrophysics and astronomy. And I wanted to just put a little plug in for my colleagues at Penn State, where multi-messenger astrophysics is a really big part of our research. And there's a wonderful review from a few years ago written by 4 of our faculty members. And so if you want to read more, I'd really recommend this review. But again, to take one of the figures from their review, you can see again this worldwide network of facilities and collaborations that's involved in making these detections. So this is a small taste. These were 2 events, and they were 2 events that were each sort of revolutionary for their communities, really the entire community. And this is just a tiny taste of what's to come. So for example, in a few years, the Rubin Observatory Legacy Survey of Space and Time, LSST, is expected to start. And this will take many optical images of the sky, the entire sky accessible from Chile every night, an enormous amount of data. And they expect by very rapidly analyzing these images that within about a minute, they'll send out probably of order millions of alerts to the community per night about potentially interesting transient events. So these bright flashes, which are now detectable, and now we have the capability to go and follow up, and they'll run for 10 years. So this is a truly astonishing way of imaging the sky that we've never had before. And again, it is coordination worldwide and involves the entire astronomical community. So as part of that social change, we're in this era where you can do science from apps on your phone to some extent, right? So you can get the app that alerts you for gravitational wave events. You can join, even as a citizen science, something like the Zooniverse, where really community efforts to analyze all of this fabulous data are underway. So it's both a change in terms of amount of data, and it's a social change, and it's a community building change in how we do science. Okay, so to summarize just briefly that part, one of the things to look for in the next decade is just a real increase in this sort of very new way of looking at the universe, from gravitational wave events where we can see, not just optical images, but optical images and gravitational waves, or electromagnetic, I should say, or electromagnetic gravitational waves and actual particles, for example, neutrinos coming in. And because these are new ways of looking at the universe, we will absolutely have new phenomena to study. And the other part of this is this attempt to do a democratization of data, where there are public alert systems and a lot of data which is not held by collaborations for a long time, but which is made public relatively quickly. And that's wonderful, assuming that we all have adequate IT infrastructure, right, to go out after this stuff. So one of the new sort of needs, is to provide researchers with very good infrastructure to take advantage of this enormous amount of data that's accessible. And of course, an entirely different talk is all of the wonderful applications of new computational techniques and techniques of machine learning to understand this very complex and very large data sets. Okay, so that's what to look for. All of those late time objects, that really rich structure, they're sort of interesting in their own right? What's out there? How do we understand the particle physics behind it? But as a cosmologist, we also want to know, why are those objects there? Where did they actually come from? Can we understand how many of them we think there should be there and why? So for example, if you look at the black holes that have been detected, both through gravitational waves. So on this image, you're seeing as a function of mass, all of the objects detected in gravitational waves. So these blue objects are the black hole mergers, binary black hole mergers detected by the LIGO-Virgo-Cogra network. And you're also seeing the electromagnetically detected black holes in pink and neutron stars in yellow. And the objects that LIGO classifies as neutron stars by mass, including the one where we know it was a binary neutron star event because we have the electromagnetic detections, are down here. there are lots of interesting things in this figure. I mean, one of the most interesting, of course, is the difference between the objects that we detect electromagnetically and those we detect gravitationally. But you might just ask yourself, do we expect these objects to be there? And where did they come from?
Sarah, there's a question in the chat. Sure. What does extreme here mean?
What does what?
Extreme mean? Like extreme.
Let's see. Why do I call these extreme events? I guess.
Yeah.
Oh, okay, sure. Yeah, good. Yeah, thank you. Yeah, I should be specific. So, extreme in the sense that these are, for example, extremely relativistic events, extremely high energy events, matter at sort of the highest accessible densities, for example, or pressure. And that's important because, for example, with neutron stars, it's a state of matter that we can't produce in the lab, we can't probe in the lab. And so at these extremes, it's sort of the most unfamiliar states of matter, even though we know perfectly well what a neutron is, right? There's still lots of puzzles about how matter behaves in these very extreme environments. I don't know if that answers the question, but possibly.
I think so. Yeah.
Okay. Oops, let me close my, okay. Right, good, okay. Yeah, good, and actually, so let me say one other thing about that. So, the other reason extreme is sort of interesting is that in these, structure formation, especially when you're talking about, the levels of galaxies and solar systems, there's a lot of stuff there. And a lot of it is hard to understand because there's so much complexity and so many ways in which you could change the physics a little bit and little interacting pieces. It's hard to pull out why those objects should be there, exactly what the formation channels are. With the very extreme events, sometimes it's actually easier, right? Because a black hole is such a special state of matter that there are only so many ways you can get it. And so the extreme events sometimes are the most accessible because it's a little bit easier to figure out where they might have come from or what their presence indicates. Okay. So when we talk about, yeah, sure. Where do these things come from? Well, we want to walk back to in time in the universe's history to this era where it's really structure formation. That's the key question. And structure formation has to do with the presence, of course, of these inhomogeneities. So we're not going to worry about that for the moment. We're just going to take it for granted that there are these sort of regions of high and low density in the universe. But how those things actually form into this rich spectrum of objects depends on the spectrum of particles that we have and their interactions, right? So if you have a hot, dense clump of matter and it's contracting gravitationally, how do you end up with something that's a very sort of cold, compact object in there? The gas has to be able to cool in order to form protostars. And then, we need something like nuclear physics so that there is this fuel to burn so that when you compactify this matter, at some point you start this burning process. So in this image, you're seeing, going from this era where it's represented as dark to where you have the first stars forming. And that's really a consequence of the rich particle structure of the standard model. So there's chemistry of the standard model at play. And then interestingly, of course, all of that rich physics that we just talked about comes from standard model processes, which is something like about 15% of all matter in the universe. So all of that rich structure that we have is just a small subset of what's out there. But the rest of what's out there, we only detect gravitationally, and we don't detect any, for example, emission of light. And this is the dark matter. So there are really many puzzles about structure formation, and in particular, what is the particle nature of the dark matter? So I wanted to talk a little bit about, what we know about dark matter, because that's been a really interesting story that's advanced over the past decade. So it's nearly 100 years since we've been talking about dark matter, and I'm showing you here a picture of the Coma Cluster, and the Coma Cluster is famous in dark matter studies because it's some of the earliest measurements that indicated that we probably did have something like dark matter came from the Coma Cluster. A galaxy cluster is sort of the most massive gravitationally bound structure in the universe. So it's not one object, it's a collection of objects, but it's sort of held together by its own gravity. And in this case, in Coma's case, it's a collection of thousands of galaxies. So this is an image, an optical image from the Sloan Digital Sky Survey of the Coma Cluster. It's not at all obvious, right, by looking at this image that it's a thing that's held together, but you look at all the motions and you find that it's a thing. And what's remarkable is that you can zoom in on these little dots. And over here on the right, I'm showing you an image from Hubble of what just one of those dots looks like, right? And each of these things is a galaxy. So an absolutely astonishing richness of structure in each of these pinpoints of light. And of course, the image that you see there, part of the reason it's hard to know what the nature of the object is that the image is incomplete. It's electromagnetic radiation, but it's only in optical wavelengths. So, the history of astronomy has been to expand the part of the electromagnetic spectrum that we collect images in, and we learn more and more about the universe through that. So for example, if you look at an X-ray image of this same region, what you'll see is a whole bunch of hot gas that's emitting in X-ray. And when you superimpose those two on each other, you get a little more of a sense of the object that's there. There's this hot gas region. There are all of these stars that are formed in that hot gas region. Famously, of course, this is barely the tip of the iceberg of what's there. If you look at the motions of individual objects, individual, say, galaxies in this cluster, and within galaxies, you can look at motions of smaller objects, what you find is that those motions are revealing a gravitational potential that cannot possibly be due to just the stars and the gas. So, you look at sort of the number of photons that you're getting and their temperature, and you can figure out roughly what mass of stars is there and what mass of gas is there. And when you try to reconstruct that, this is from a paper in 2003, the models tell you that, the dashed line here is the hot gas that you're seeing in pink. The dotted line here is coming from all the galaxies, all the optical image. And yet the total matter that must be there is way up here, almost an order of magnitude higher. So basically, the vast majority of the matter that's giving you the gravitational well in which this object is forming and living is something else that you can't see in any of these images. That's a pretty old story. What's new, and this is an image from last year, is our ability to do this type of mapping on just extraordinary scales. So here you now see a picture of the sky where you're seeing, right, many, many degrees. This is an image that was put together by the Dark Energy Survey. And you're seeing two things. You're again seeing a superposition of gravitating matter and light emitting matter. The gravitating matter is in the color scheme here. And so dark, black and purple is underdense regions where there's not much matter. And light, yellow, orange, is overdense regions where there's a lot of matter gravitating. And this image was actually made by reconstructing how light bends. So, you can look at the motions of objects in a gravitational field, or you can just look at how light is bent. And that gives you a much more detailed and nuanced view of the gravitational field. And then what they've done on top of that lensing map is to take sort of a random sampling of known galaxy clusters. And this is what's shown in the greenish yellowish circles, and superimpose those on the map. So they're not showing you everything because that's way too much structure, but they're showing you a representative sampling of things, with the point being that you see more stuff, right? More galaxies, of course, in the overdense regions. And you see these darker regions that are relatively empty comparatively. But again, there's not the interplay between those two things is sort of interesting. How did the galaxies form? Why are they there compared to the potential well? And just to give you a sense of scale here, this little blue or aqua-ish circle is zoomed in here. And then they've again given you more structure on top of this region of the map. And here you can see even more clearly sort of a void, a cosmic void, and a structure of overdense regions that are sort of strung together here with the galaxies and clusters superimposed. So our ability to make these maps of the whole universe is rapidly increasing. And by making these maps, we understand in more detail what the particle physics is and what the interplay between these gravitational potentials and the formation of structure is.
There's a question in the chat.
Yes.
How is the bending of light measured?
Right. So okay. So this is really interesting, right? So you have to do this, of course, statistically for an individual object. If it's an extreme case, so an extreme case of a very strongly lensed event, you might actually see two images of the same object, right? And you would know then that what you're seeing is a lensed image, and that there's some lens, some big bunch of matter in the middle that's bending the light. But you don't see that all that often. But of course, most light from most objects is bent in some way, because of course it passes through a matter field on its way to us. So how can you pull that out? And so that's sort of a statistical game of figuring out, for example, how shapes of galaxies on average are distorted by the presence of a gravitational source. And so it's there was a lot of analysis and machine learning that went into making this image, and of which I'm not an expert, but basically you want to look for distortions of images, and you can only do that in sort of a statistical sense to get the answer. Those, okay, good.
Yeah, that's
sure. Okay, so that's great. Those images are wonderful, and a lot of the goal of those images is, of course, to just make them, but also then to try to use that information to understand what is the dark matter, what is this stuff made out of, because that's so key for the structure in our universe. So the picture I'm showing you here is a very standard picture in the dark matter community that has to do with how can we figure out what dark matter is. And it starts from an assumption that's important, because that affects your, how you think about what dark matter, how you should detect dark matter. But the assumption is that the dark matter interacts somehow with standard model particles. So the image shows an example of two dark matter particles and two standard model particles, and they can have some sort of interaction. So this blob in the middle is just interaction, boom, whatever happens. If you read this diagram in various directions, it gives you a sense of how you might go about looking for this interaction, which will then tell you something about the nature of the dark matter. Let's start at the bottom, where we go from the dark matter side to the standard model side. So there you might imagine that somewhere out in the universe, there are two dark matter particles. They collide together and they produce some sort of standard model particles. If we look for example, unexpected light, that could be a signal, some sort of byproduct of this collision that is a signal of what the dark matter actually is. And in the spectrum of light, for example, the energy, that might give you a clue of the energy of this collision, which would give you a clue about the masses of these particles. So this is a technique for dark matter studies that's called indirect detection. You basically look up, into the sky for unexpected light. That's great. That's a great idea. The problem is the sky is full of unexpected light, right? The galaxy is a very complicated place. It's hard to understand what all the light should be. So there have been, hints over the years about light that may be from dark matter annihilation into stuff that's the standard model, but we don't know for sure. There's no clear signature there yet. On the other hand, if you read the diagram going up in this direction, you might imagine that there's a bunch of dark matter out there in the universe. It's zipping around. It passes through the Earth all the time. And if we build a big, carefully controlled vat of standard model matter, we could hope that the dark matter is going to hit it sometimes, and we'll be able to see the signature where then the dark matter particle goes off and the standard model particle goes off. That's called direct detection, because we're really seeing directly the impact of a dark matter particle on a standard model particle. And that's what people are doing when they go underground and dig into old mines and make big vats of things like xenon, a pretty non-reactive gas, where you can see the recoil motion, for example, of the xenon nuclei in this process. That's been a very big program for dark matter studies. And again, so far, nothing has been found that way. Finally, if you read the diagram from the yellow side to the gray side, you might say, well, okay, if there's really some connection there, we should be able to take our standard model particles, smash them together, and see something that's related to dark matter production. And that something usually is missing energy. You have all of these detectors around your collision centers in colliders, and they're designed to detect all the standard model particles. But if something gets out, some energy gets out that you don't see, that would be a sign of something like dark matter. And of course, collider studies have been done in many contexts, not just LHC, but also other things that look for dark matter in other various energy regimes. And again, nothing has been found. So it's a puzzle about what the dark matter actually is. And I wanted to give you just a little bit of I don't know, there's a lot of sociology in physics, right? So why are we looking for dark matter in the ways that we are? Part of it has to do with what our ideas for physics beyond the standard model have been. So I've got here a huge range of energies in electron volts, all the way down from masses of standard model particles, which live sort of in this region here, all the way up to the Planck scale, where we know for sure that we don't understand things. And our best our highest energy particle colliders, the LHC, operate here somewhere around a TeV. And of course, the LHC had the great success of finding the Higgs boson and perhaps the disappointment of finding not anything else. So, let's say 15 years ago-ish, roughly when I was getting my PhD, we had a lot of wonderful ideas for what might live up here at slightly higher energies. And those ideas included things like supersymmetry, extra dimensions, consequences of things like string theory. And these are all wonderful, beautiful, compelling ideas. But the ideas for physics beyond the standard model that came out of all of this haven't quite panned out in the sense that you predict that we might have found a lot of things at the LHC, for example, or at dark matter direct detection, which we didn't find. And so we really probably need new ideas for what we think explains why the Higgs is there at the mass that it is and nothing else is there, that will help us figure out how to go forward in dark matter studies. So I'd say it's a really interesting time in particle physics right now, because sort of this rush of really big, exciting ideas didn't quite pan out. It's not to say they won't, they're still wonderful ideas, but it's not quite clear that they're panning out in the way we expected in terms of telling us where to look and find new particles. And we may be on the verge of needing some new ideas. And at the same time, we have this explosion of astrophysical data, which may be able to help us pursue some of those ideas. So one thing you might do is to go back to a perspective that we've had in cosmology for a long time, which is this perspective over here on the left, that the most important interaction, in the sense of relevant for detection and relevant for cosmology of dark matter, is with the standard model. And this has been the story of, how do you produce dark matter? You have some process where you had dark matter and standard model physics or particles in thermal equilibrium in the early universe. You do sort of a freeze out scenario where as the universe cools, the expansion of the universe is more important than whatever that interaction is. And you can explain why we have the amount of dark matter we have based on that. And then by that same token, you want to build these kinds of detectors like direct detection experiments where you go and you look for that key interaction. It could be that it's time for a change in paradigm where we don't necessarily focus on dark matter standard model interaction as the most important cosmologically and observationally. But think about the fact that so far we have lots of evidence for gravitational interaction between dark matter, whatever it is, and the standard model. And here, instead of a particle, I really want to focus on the fact that we have this complex structure of particles in the standard model. And all of the physics we've talked about comes from details within this sector. So it could be that, in fact, somehow the most important interaction for dark matter in terms of cosmology and in terms of observation may actually be within the dark sector itself. So rather than thinking about, the one next stable heaviest particle beyond the standard model, it could be that there's a sector, a whole collection of dark particles that don't couple very directly at all to the standard model. So there's lots of interesting stuff sort of going on in the dark universe over here that's only gravitationally communicated to the particles over here. This would be a big change in perspective, and it would suggest that we look in different areas for signatures of what the dark matter particles are. Okay, so I'm going to talk about this just a little bit because it's sort of my favorite ideas right now. So now this talk goes away from generic overview to my particular interest for a few minutes, but I can't resist. And I want to say why I've talked about chemistry here. Chemistry, even though as physicists sometimes we don't want to be chemists, we're a little snotty that way. We should kind of back off on that because the chemistry is really the whole reason we've got interesting stuff. The gas, as I said before, has to be able to cool in order to form protostars, and the stars need their fuel to burn. So the fact that we've got this interesting periodic table, and this curve of binding energy per nuclei that we've got is really key to all of the structure that we see. And it could be, in fact, that if dark matter has somewhat of an interesting particle spectrum, that it has its own chemistry, and that may end up being the key to how we understand it, because it's really the chemistry that generates the rich spectrum of small scale structures. And those we can detect gravitationally, even if we can't detect a direct interaction between dark matter and the standard model. So just to give you one example, that's been a lot of fun that my group has been working on recently, is to imagine that dark matter is made up of a set of particles And in a really simple case, you might imagine that they're something like an electron, something like a proton, right? So oppositely charged fermions, something like a photon, and a dark version of electromagnetism. The numbers don't matter, but you might imagine that these particles are all maybe somewhat heavier than standard model particles. What's interesting about this is that you can, if you change the mass of the proton, so the dark matter, the dark sector has a heavy fermion that's somewhat heavier than our proton. You change the Chandrasekhar limit for black holes. And if you have somewhat heavier, cosmologically relevant fundamental fermion in the dark sector, you open up the possibility of generating subsolar mass black holes. These things, it turns out, are detectable with LIGO. And so you can go and look for them, and their presence or absence is really a direct measure of particle physics of the dark sector. Just this fact here is, pretty, has been known for a long time. But what's interesting about this model is that you also can form a dark version of hydrogen, atoms and molecules. And this provides the same sort of cooling channels that you see in the standard model. So this very minimal, but in some sense non-minimal, right? This is not cold dark matter, but still very minimal particle content allows black holes to form dynamically from dark matter in principle. And those black holes can have a very distinctive signature. They can be subsolar mass. So that's sort of a, those are two statements you can make, but the question is, can you actually form enough of those black holes for it to be relevant and interesting? And you might remember that, in the standard model, very little of the total matter out there actually ends up in black holes, just a small fraction of a percent. And yet that's enough for us to have those fabulous order 100 events from LIGO already. So we don't need a lot of dark matter to be able to cool to potentially get dark black holes. But you have to check, can the dark matter cool? If it can form black holes, what are the masses? They're almost certainly not Chandrasekhar limit masses because they're formed in this dynamical cooling process. And so their mass is set by sort of the scale at which the gas breaks up into little chunks and the gas fragments. How many would there be? Could they be in binaries? Could those binaries actually be merging today? So a few years ago, based on some basic notion of chemistry for this dark matter that had been in the literature and some old arguments about early star formation, with Dongyi Zhang and a student, we went ahead and estimated, how many subsolar mass black holes could be there in this scenario. And what we found was for various masses of a heavy dark proton, and the mass of the dark electron was chosen to sort of satisfy various other constraints on dark matter because it can't be too interactive on large scales, right? We know we have these dark matter halos. We found that there could be rates for LIGO, and these were sort of under different assumptions about how much of the dark matter could cool and form black holes. Is it, 10 to the minus 3 of the dark matter is in black holes or 10 to the minus 5? We found these rates for LIGO, and with certain percentages of the black holes that might be subsolar. So these are high enough rates that this is pretty intriguing, and we decided it was worth further study. So since then, we've been participating in searches for subsolar mass compact objects in LIGO. And again, it's sort of interesting. LIGO has the ability, right? They have the data to observe these, in spirals of these very light objects. It's hard to do that analysis because the in-spirals can be very long, and you can only see things that are close because the lighter objects have sort of a fainter signal. But the data's there. But sort of for sort of standard model centric reasons, a typical analysis stops right at about a solar mass, which is where you expect neutron stars and standard model stellar process black holes to be. But there's no real reason for that. Beyond just computational complexity and pro-standard model bias, I guess I would say. So we can go ahead and do the search, and that's an important search that LIGO can do. That's a direct search for physics beyond the standard model. We had some fun looking at an unusual low mass merger event to see what we would learn from that. But mostly we're trying to improve on the sort of very crude estimates that we got in the previous study and figure out if we can actually, in a more sophisticated way, work out how likely it is that you would have something like ultra compact objects form dark matter. So this has been a lot of fun, but mostly I bring it up just to illustrate the fact that we have this really great era where we have this new data, which in principle is developed to detect very late universe, messy standard model objects that at the same time may end up being, because it's just gravitational, give us very clean new data that's really relevant for the particle physics of dark matter. So this is a new era in dark matter. I just wanted to mention, because you can hardly give a cosmology talk without that, the study of structure is one way to go after dark matter, but there's also this interesting conflict in the data that's playing out right now over the measurement of the expansion rate, the Hubble rate today. And there's a difference in the expansion rate that you infer from CMB, which in many ways you expect to be very clean because the physics is not that complicated compared to late universe. And on the other hand, when you look at late universe objects and try to get measurements of distances to measure the expansion rate today, you find different numbers. And this has been a tension that's been growing for quite a number of years. I just wanted to put a summary slide of those measurements. There's too much data here, too much detail for me to go through. You can look at these papers if you want, including one from December. But the basic upshot is, after all of this, you see this sort of pink bar over here, which is what CMB prefers. And you see this gray bar over here, quite a distance away, which is what calculations based on sort of local universe structure are measuring for the expansion rate today, and they're very different. And so an ongoing conversation in cosmology is this the first evidence that there's some new ingredient in the model that we need to add in order to understand the expansion history, right? Because CMB is early time and you make these inferences to today, and then these are late time complex objects, but late time measurements. Okay, so let me just summarize this bit about structure to say that, next 10 years or so, what to watch for. One of the things to watch for is what is the resolution of this tension in different measurements of the expansion rate? Is it a signature of new physics? Is it something in our modeling? Is it something in systematic understanding of the objects that are out there that will change? And then I think the other thing to watch for is, if you think back to the maps I showed you of the dark matter distribution, the ability to map out the matter on a huge variety of scales, and including within a particular galaxy and small galaxies like dwarf galaxies, those things are going to tell us a lot about where dark matter is. And where it is of course affected by its interactions. So if it really has self-interactions, the structure on small scales will help to tell us that. And at the same time, looking at sort of very late universe small objects, which you think is the realm of things far removed from cosmology, exoplanets or neutron stars in the late universe, these might actually suggest to us new ideas and new directions in dark matter, at least new constraints. And then I didn't talk about the thing that people love to talk about, which is dark energy. We will still make progress on measuring dark energy, sort of pushing back to higher redshifts. And I didn't talk about it because it's not really clear where that's going, I guess. The story is pretty much the same. Is it a cosmological constant? Why is it so small? What is the dark energy equation of state? We're sort of stuck on that, but we will have improving data, which may change that story. Okay, so in the last bit, and I'll try to take a reasonable amount of time here. I wanted to go even further back and say, for the moment, we've taken that initial spectrum of fluctuations for granted. But why is it there? Why does it have the features that it does? How did the universe get started? Why do we have this universe that seems to have started in a smooth, homogeneous state with sort of this, very nice pattern of fluctuations over vast scales that's uniform, which has evolved into this very rich and dynamical universe today? Why is that the universe that we have? Should we have expected that from our understanding of the basic laws of physics? And so let me just remind you of the basic conundrum here, which is the horizon problem. And that is that when you look out at the cosmic microwave background on all the scales that we see, it has a remarkably uniform temperature of 2.725 Kelvin. And it's the same everywhere that you look. And when you look at the spectrum of deviations, and that's what you typically see in a map of the CMB. So these are the hot and cold spots once in comparison to this 2.725 Kelvin, that spectrum of fluctuations, again, has a very long wavelength structure across the whole sky, and it's the same across the whole sky. And that's confusing because when we look at the CMB, we see basically, light from points the farthest away, the light has to travel from the CMB to get to us, and that's how much of the universe we can see. That's dictated by that light cone, if you like. But if you look back at points on the CMB on opposite sides of the sky, and you ask, what information did they have? Did they share information in order to arrive at the same temperature? You find that they don't. The sort of information or the light cones associated to 2 points on the sky don't intersect. And this shows 2 opposite points on the sky, but it's actually really separations of about 2 degrees on the sky that didn't have causal contact in sort of the standard hot Big Bang picture. And so that makes you think, why should those things be the same? Why should the temperatures be the same? Why do we see this very large scale pattern of power and fluctuations? That's an old problem, and it's an old problem that the community has largely centered around a resolution to that problem, which is an era of inflation, which is an era of accelerated expansion that preceded this sort of hot Big Bang phase and is responsible for creating those fluctuations and creating them on scales that are very large compared to what we would have seen as causal contact in the hot Big Bang scenario. So there's this canonical cartoon of inflation where what do you need? You need accelerated expansion, which means you need a universe that's essentially dominated by something that's almost a cosmological constant. So you draw a picture of energy that's almost a constant potential, and then at some point, that can't be true anymore. That can't be the shape of the energy, so that inflation actually ends. So we draw these cartoons, and the magic of this cartoon is that in this era of accelerated expansion, this sort of nearly de Sitter space, the thing that you get for free are fluctuations of the matter field sourcing the expansion. It's usually just a simple scalar field in the simplest realization of this. And fluctuations also in the scalar degrees of the metric, so that things that control sort of the scalar curvature, which is related to density, that you get for free. So the nice thing about this picture is that you get sort of a causal explanation for why you have this spectrum of fluctuations. And it's sort of fundamental. It's quantum mechanical origin, which is sort of very appealing because it seems very fundamental. And then it's these fluctuations in the metric that source all the density fluctuations that give rise to galaxies, right? Everybody couples to the metric, everybody sees gravity, and the temperature fluctuations in the CMB have the same origin. And because you have all metric fluctuations, you also have, in principle, primordial gravitational waves. So this is the sort of canonical origin story for everything that we just talked about in the late universe. I'm going to get just a tiny bit technical here to explain a couple things. This is the way we describe what the metric is, right? The way to measure distances, the background space-time is during this era of expansion. And the important thing is just this scale factor. And you can just think of this as the size of the typical ruler in that era, this scale factor A. And the evolution of that scale factor is really the important thing that we follow, or that we, if you like, we actually design into the model. We want this space-time expansion to behave in a certain way in order to explain the data that we see. And so somehow we want the dynamics of this matter field to generate for us the appropriate background fluctuation. One thing that's important is, we see a finite universe. We only see so much of the sky. So we know inflation has to explain why the largest scales we see have the same temperature, why they were in causal contact. But it seems a little bit special to assume that things change, just beyond what we can currently observe today. So if there's some largest scale, there's some time on this potential, some amount of inflation that explains the largest scales that we see today and why they look the same, it would be sort of silly to imagine that things change dramatically right back here. Why is our time special? So typically we think that there's probably more inflation, or in other words, there's a much bigger universe out there that statistically looks like the universe that we see. And it just happens that we can't see all of that yet. When we test this picture, we typically use the CMB, and then of course, large scale structure. But interestingly, we only can have good statistics that really test this phenomena and not all the messy late time physics on pretty large scales. And so what we measure actually just probes a tiny little part of this picture, right? We draw this whole big picture with lots of inflation to explain what we see, but it's really designed to explain this data right here. And that's where we really test it. The thing that you see when you see comparisons between inflation and data is really this spectrum of fluctuations that I talked about in the metric and the scalar field. Because the expansion is nearly exponential, we often write the scale factor this way with the Hubble factor here. And what you see is a measurement of a 2-point correlation in Fourier space, right? So you could either look at the sort of spatial statistics for those hot and cold spots, or you can take the Fourier transform. And that's what we often do to make predictions, is take the Fourier transform. And we look at the correlation between spatial curvature in 2 different momenta, K1 and K2. And this is a really simple form. It has a simple form because the universe is very nearly isotropic and homogeneous. So it really is just a function of the scalar momenta, K. And this K cubed is a dimensionality. So all of the interesting stuff is in this power spectrum up here, which is that sort of dimensionless power in each wave mode, in each scale on the sky. That's the thing that's measured really precisely. And inflationary models, it's very simply given by the Hubble factor during inflation divided by the Planck scale. And then this parameter epsilon, which basically tells you how different the expansion is from exactly static, like an exact cosmological constant. So that's pretty important. It tells you the deviation from exact exponential inflation here. And basically what it tells you is if that inflationary error was exactly de Sitter, it actually wouldn't be interesting. Those fluctuations in density wouldn't be real. They would be sort of a product of your coordinate choice. So this is the thing that's measured really well in inflation. And basically it tells you there's some dynamically evolving matter that's sourcing the expansion. When you see the CMB, you see this complicated wiggly spectrum. And the complicated wiggly spectrum is because you take that spectrum of fluctuations from, or the way you fit it, right? The way you get the theory lines is you take that spectrum of fluctuations from inflation, and then you ask what happens to the fluctuations as they come back into causal contact in the universe and they start to evolve all the way until you get the CMB, right? Which is actually this spectrum of photons that's released when the photons are no longer strongly coupled to the matter there. So this wiggly spectrum has a lot of late time physics, but basically what it is you can, if you back it back to inflation, you just get a measurement of how much power there is in each K mode in those fluctuations, and you map that back to a picture of the potential. The other part of the story is not just these temperature fluctuations and scalar fluctuations, curvature fluctuations, but actually gravitational wave fluctuations. So the off-diagonal terms in the metric. And again, the simplest thing to compute is just some 2-point correlation between different momentum modes of these tensor bits. And again, there's some homogeneity and isotropy that tells you this is just a function of the wave number K. And this is just a factor of dimensionality, right? And then what's interesting is the power spectrum, the amplitude of fluctuations in each wave number. That we haven't measured, that we've constrained, but we haven't measured. And it's a little bit different from the scalar fluctuations because it doesn't depend on that tilt. It doesn't depend on how different you are from exact exponential expansion. It just depends on the scale factor, on the Hubble rate during inflation. And so it's really something that tells you just the energy scale of the problem here. People focus on measuring this, but usually they phrase it as a ratio between the scalar fluctuations that we've measured and the tensor fluctuations that we haven't, but that we'd like to. And in simple inflationary models, this epsilon, this deviation from exact scale invariance, is what tells you how big the tensor to scalar ratio should be. So that was sort of a long-winded introduction to one of the things that's sort of on the horizon for the next decade, which is an improved search for primordial gravitational waves. And this is one of the main goals of current CMB facilities and sort of next generation facilities, including CMB stage 4, which is in progress. This is the latest constraint, and the constraint is usually given as that tensor to scalar ratio compared to the spectral index, which is basically how different from exactly scale invariant that power in mode is. And if this was 1, it would be exactly scale invariant, which it's not. So this is typically the way these constraints are presented, and they're presented also. People typically plot a bunch of inflationary models on top of them, so you can see which things are constrained and which things aren't. So a measurement of primordial gravitational waves would tell us a completely new fundamental scale in physics, which would be this inflationary scale. And it would also be sort of, again, a new phenomena, right? If the picture of inflation is right, those fluctuations should be there, but actually detecting them, and they're detected through the polarization of the microwave background light, would be really phenomenal. Okay, I had a lot more I was going to say about that. I don't think I will. I think I'm just going to remind you this, what I just said in words, is that this would give us a completely new scale of particle physics, right, h/m Planck. And it would also be related to the scale of inflation, what the energy was in that potential during inflation. If primordial gravitational waves are detectable, this number R can't be smaller than about, 10 to the minus 3 or 5 times 10 to the minus 4. So if they're detectable, then the energy scale of inflation is somewhere up around the gut scale, 10 to the 16 GeV. And just to remind you, that's a very high energy, right? Somewhere up here, far above collider energies, far above, where we look for new particles, even astrophysically. And so that would really be a sort of an interesting data point in the sense of particle physics. Okay, I'm going to skip this discussion about what it would mean, except just to tell you that if we detect primordial gravitational waves with an amplitude, that's 10 to the minus 3, 10 to the minus 2, in some ways it would be surprising. And the reason it would be surprising, I won't go into in detail, but basically you can write this number in terms of the region, or the sort of the length over which that potential is featureless or flat. So whether you have a potential that's relatively flat over sort of Planckian lengths, or a potential with a lot of structure. And there are lots of arguments for why you might expect a potential with more structure than this, having to do with your expectation for degrees of freedom that are relevant up near the Planck scale. And those arguments have been made in a way that's relatively model independent. So even though they sort of grew out of arguments in string theory, people have pushed them toward an expectation that's more like an effective field theory expectation about structure. So the takeaway that they want you to get from this is just that if we do detect primordial gravitational waves, that's going to give us some interesting information that informs how we think about inflationary models, and in particular, how we think about them in a quantum gravity sense. What are the degrees of freedom that are active at very high energies? And if we detect them, it almost might be like detecting a symmetry, because there's sort of less structure in the potential than you might naively expect there. So that's something to watch for. Okay. I'll just say for just a couple minutes that all of that discussion had to do with this canonical cartoon picture of inflation, but I'm not sure that we actually really got to the heart of the questions that we want to address with early universe cosmology. We got to them in sort of this practical sense about tensor to scalar ratio, and does it tell us something about degrees of freedom and symmetry at high energies? But there's sort of these canonical questions about inflation and the original era of the universe that have been around for as long as we've been asking these questions. And sort of the most mundane version is, what are the particles that actually sourced inflation? Was it some particle I expect from string theory, from supersymmetry, from whatever? And is it natural? If you looked at all of the possible things that could happen at very high energies, do you expect to have this rather smooth potential that generated lots of inflation to give us this universe that's very similar on such scales? And if you did, do you expect inflation to always be a feature? Could it go on forever in some parts of the universe? And is inflation really our only idea to explain this data right now, or could there be something else? So these are the sets of questions that are sort of bigger questions that we'd like to address in early universe physics. And the only thing I'm going to say about this, again, it's sort of a long story, but I don't want to take too much time, is that, this picture where the universe that's generated by inflation is much larger than what we can observe, but statistically the same, is really interesting. And it's especially interesting if there are correlations between fluctuations that we can observe and fluctuations that we can't. And in that origin of fluctuations picture, that quantum picture, basically in the quantum fluctuations, were there interactions that were coupling the quantum fluctuations on small scales to quantum fluctuations on larger scales? And, if so, what it suggests is that we observe just a statistical sample of some bigger universe, which means there's a really interesting inference problem in going from what we see to what actually may have generated all of the structure in the universe, because we can only see so much. And it also means, I apologize for including way too many slides. It also means that in the quantum picture, what we see, the modes that we see are coupled to other stuff. And that other stuff is not in the UV. So it's not clear that it's actually our standard happy low energy effective theory that describes the physics of what we can see. In the context of inflation, those modes, at least in some sense that's possibly not observable, but still is the correct physical picture, are really part of an open quantum system. And that's a feature of gravitating systems, that there are often boundaries, there are horizons or, space, parts of the space that you can't see that aren't, in the UV, they're just parts of the space. And so I think as we explore the quantum picture here, there's going to be a more increasing emphasis on understanding open quantum systems. Okay, so that was too short of time probably for all the issues there. But what should you watch for in the next decade? On a observational sense, one of the most important things will be to see what happens in terms of primordial gravitational waves. Could they be detected, or how will the constraint improve? In the theoretical sense, coming back again to this idea of what are ideas for physics beyond the standard model, we found the Higgs and nothing else. It will be interesting to see what happens in terms of particle physics for inflation, and whether we're sort of happy with the spectrum of ideas we have, or whether new ideas emerge. And in sort of a bigger picture, even earlier universe perspective, cosmology and inflation in particular, because it's nearly de Sitter space, and it's also the same universe nearly that we think we have today with accelerated expansion, those types of spacetimes promote sort of a different relationship between what questions we ask from quantum information science and what we ask in the context of gravity and cosmology, that are different from the very fruitful but paths that have been studied before in the context of ADS CFT, for example, and also in the context of black holes. So I think I would watch in the theory space for sort of new ideas to emerge in the connection between quantum information and gravity and cosmology. Okay, all right. I've used enough of your time probably, so let me just summarize and say, that in a sort of practical operational sense, the thing that's astonishing, of course, continues in cosmology to be data and techniques for analyzing data, computational techniques, all of that, which I've hardly discussed, but which is really sort of the key. But what that means in practice is that we will have enormous numbers of measurements of new gravitational wave events. We will have probably exotic events uncovered by multi-messenger physics. We will have unbelievably detailed maps of the matter content of the universe, which should help us probe the particle physics. And it will be very interesting to see if this lambda CDM paradigm, which has stood solid for quite some time, but which has these pieces which are so poorly understood theoretically, will remain, whether it will be revised, and whether we'll make progress in understanding the particle physics, the microphysics of the components of our cosmological picture. Okay, I'll stop there. Thank you very much.
Thank you, Sarah.
Yeah, we should first thank Sarah for this incredible overview of the whole field of cosmology. And we had a couple of questions, but we have time for a few more questions. So you can write in the chat, or you can just ask directly. So there is a question, Sarah, in the chat. If LIGO observes a subsolar binary black hole merger composed of dark matter, can you distinguish it from a primordial binary black hole?
Yes, good. Thank you. Yeah, I didn't talk about this. This is interesting. So, as many of you know, there's sort of another idea which has been around for quite a long time about how you could produce subsolar mass black holes. And that is to have in the very early universe, very large overdense regions. So, that spectrum of fluctuations that we have from the CMB doesn't produce very many of these things. But if you had much stronger fluctuations, you might have these sort of primordial overdense regions that would be so overdense that they're black holes. Right. So, and those things, in principle, depending on what scale the fluctuations operate, could produce for you a subsolar mass black hole. So just from LIGO's perspective, a black hole is a black hole, and you measure their mass and their spin, and then you're pretty much done. So from just the sort of mass distribution, no, you can't distinguish them. But of course, the scenarios are very different in a variety of ways. One of them probably is redshift distribution of black holes. So in the primordial black hole scenario, you got a bunch of them and they've been there for forever, so you're done. Versus in the sort of dark matter scenario, these things form astrophysically. So they may form as early as redshift 20 or 30, but they're forming astrophysically, and the binaries only have enough time to evolve since those things formed. So you would certainly expect probably a difference in details. Now, the thing about primordial black holes is because we have no other constraints on small scale power, you can pretty much put whatever you want in terms of small scale power and clustering, and you can get lots of stuff out. So it's possible you could basically mimic any distribution of dark matter black holes with a primordial scenario. Of course, a dark matter scenario that's dissipative doesn't just produce for you primordial black holes. It does all kinds of other things as well that affect structure formation. And so the real, I think, distinguishing feature of these scenarios would be how adding dissipation changes other aspects of dark matter structure. The black holes are only a small fraction of that, right? In that scenario, very small fraction of the dark matter is collapsed to black holes, but the dissipation is relevant for all small scale structures. And so that's where they would be distinguishable. And I'll just say one other thing about perspective between these. When you do primordial black holes, the new physics is in why do you have this particular spectrum of fluctuations at small scales? And that's something about inflationary physics again. And in the dissipative scenario, the new physics comes in having a sort of a complex dark sector that has particle interactions. So it's a very different way in which the new physics comes in, which might just help orient thinking in terms of how you would think about the comparing these two scenarios. I'm happy to say more if people like, but yeah, thanks.
Thanks. Any other questions? Yeah, there's.
Oh.
Yes.
Yeah, I have a question regarding the dark sector chemistry. You mentioned there can be different types of objects. One property it must have is that it is much less clumped compared to the normal matter that we see, because dark matter halos are much bigger than the galaxies. So what properties of whatever interaction in the postulate? For example, I may simply take a copy of the standard model and just change some parameters. Because there must be some short range interactions, some long range interactions. Gravity, of course, has to be there. Given that, what changes should I make to explain this basic qualitative feature that clumping is far less within the dark sector compared to the usual sector?
Yeah, good, thanks. Yeah, great. So this is the primary constraint on these things. As you say, we know that the interactions have to be somewhat less than in the standard model. And so it's actually a really interesting question about how to phrase these constraints. For a long time, people just focused on cold dark matter and it wasn't a question. If you start asking about about interacting dark matter, where you think about sort of just elastic scattering, which was a big sort of the next stage that people did, a lot of the constraints are phrased in sort of the cross section per mass of the dark particle, typical mass, so sigma over m. And then you use things like anytime you have interactions like a bullet cluster, and you can test how well standard model matter interacts and gets stuck in clumps versus dark matter, which seems to pass through. You can phrase that as a constraint of the cross section, the self-interaction cross section of the dark matter. And basically that's the type of constraint you have to calculate for all of these scenarios. And actually, for the case I mentioned, the atomic dark matter scenario, people have done versions of that calculation for many, many years. When you have dissipation, you might phrase it slightly differently and phrase it as an energy loss rather than self-scattering. You might phrase it as dissipation constraint or cooling rate. So it becomes a little bit more of a dissipative calculation. And then you have to check for all the scales over which you have constraints on dissipation or interaction, does your model satisfy those criteria? So it's easy to say in words and surprisingly complicated to do from data. But basically all the models that people consider now pass those basic criteria. They give you halos on large scales. The interactions aren't so strong that they violate things like bullet cluster constraints. And there's still a remarkable amount of freedom for having interactions that are relevant on smaller scales.
You put in the mechanism of dissipation as essentially radiation?
Right, exactly. So if you have, for example, collisional excitation. So you have a hydrogen atom, it gets hit by a hot electron, it moves to an excited state, it radiates away a photon. Exactly. So in this case, a dissipative mechanism would be radiation. Yeah.
Okay, thank you.
Thanks.
Sarah, there's a question in the chat. As you mentioned, we can measure dark matter using unexpected light, but how do we know which light is unexpected?
Yeah, this is the fun game, right? That's been played in this field for many years now. But one thing that you might think is unexpected is if you see something that looks like a sharp spectral line. So you see something at a particular energy scale, lots of extra radiation, at a few keV or something, you might think, oh, that's definitely a signature of some sort of annihilation because it's only at this fixed point in the spectrum. And maybe you think there's no other way to produce that sort of spectral line. And that's the kind of thing that people have looked at, over the years is there some unexpected radiation that doesn't seem like it has a spectrum coming from an astrophysical process. Of course, what's happened is you realize that there are all kinds of astrophysical processes, and it can be very hard to determine what's unusual versus impossible in astrophysical scenarios. So it's an interesting game. It's a very hard game to convince yourself that there's no possible astrophysical mechanism to produce some of this light, because it's light, right? You got all kinds of crazy stuff going on in a galaxy. And that's where you sort of win with the gravitational signal, because there just are no, for example, subsolar mass objects possible in stellar formation channels. And so even though the formation may be complicated, the signal is clean. And that's what's nice about those.
Okay, any other questions? There is one raised hand, I think. Anand, yeah, you can just ask your question directly.
Yeah, Professor, I really enjoyed your talk. Thanks so much. My question's about actually like how we infer what the events are from gravitational wave observations. So as far as I understand, there's like no magic bullet or anything which tells us what the event is just from the data, the observations. So as the gravitational wave astronomy grows over the next decade, will the number of different types of phenomena we simulate or have to consider, like to sort of expand a library of what the possible different waveforms and stuff are, also have to grow a lot? Or do we have most of the waveforms that, or at least do we know most of the things that we can expect to observe already?
Yeah, great. That's a multi-layered question, right? So I think if you take sort of a narrow view, and this is not my primary field of expertise, so take my answer for what it's worth. But if you take sort of a narrow view that you take compact objects within general relativity, then the waveforms that we expect, we know pretty well. And that's where they come up with the library of models that they use. Now, then you can ask, okay, but how do we know that general relativity is correct? And how do we know that there, for example, is nothing below a solar mass? And how do we know that there aren't exotic neutron star-like objects? Then, yeah, we don't know, absolutely. And so I think how we proceed in this field will depend a lot on what we see. If we see a typical spectrum of black holes like LIGO has seen, then the focus is really on what are the progenitors, how do you make those things? But we assume that they're sort of within the standard paradigm. Of course, on the other hand, if you see something at a funny mass, or, as we get better at looking matter effects, if you see something with unusual compactness, unusual sort of matter modes, you would go back to the drawing board and start to simulate more complicated things. So I think, it's really actually interesting to go and look again at the predictions for rates for LIGO in the year before they made a detection, right? The predictions are all over the place. It's amazing how much, even when you know the objects and you know the standard model, you cannot predict the rates very accurately. So I think really the data will drive what happens in terms of the theory and the modeling. And the flip side of that, I apologize, I'm going on a long time, is that, ways of looking in the data for things that aren't just standard waveform filtering are also really important, so that you make sure that you're not, biasing yourself to only see what you expect to see because you put in models only generated by, by general relativity with standard mass sources. So people have creative ways to look through the data and look to see if they're missing a signal that looks unexpected in some ways, and that will also increase. So data analysis techniques, and then those will drive, I think, what direction the theory and modeling probably goes.
Thank you, Professor.
Thanks. Okay, I think we had enough questions. So maybe we should thank Sarah once again for a wonderful talk.
Thank you for having me.
Thanks a lot. Yeah. So now, Madhavan, yeah, again.
Yeah, thanks, Sarah, and thank you for joining us for this event, and all of you in the audience as well. So look forward to seeing you again tomorrow, same time, for another talk. And good night from our side, and good morning, I guess, Sarah.
Thank you.
Bye.
Bye.